So by the way, this is so this paper. I mean, this paper describes TraceMonkey, which was the first version of Firefox just-in-time compiler for JavaScript. So JavaScript was interpreted for a long time, and then because of that caused a lot of performance issues, and people were trying to build a lot more sophisticated things on your browser, like Gmail and mailing things, so mail clients and mapping clients. So people they basically needed to get better performance, and Firefox came up with TraceMonkey, which then, this was the first version, eventually got updated in a variety of different kind of systems, and then Google had their own version, which is V8. So this describes TraceMonkey, which is the first version of Firefox's, just-in-time compilation. So how does it work? What's the key insight? Huh? What? Hot code. Hot. If it's hot, make it fast. Okay. So so. But how specifically? So can someone kind of describe kind of how it works? How does it? So at a very high level, if you were to describe this thing like, if you were to give someone an elevator pitch, it's like you have 2 minutes to describe the whole system. 2 minutes. What?
It's a long time.
Okay, 30 seconds. Blame him. Okay, you got 30 seconds. Oh my gosh, I can't do it in 30 seconds. Okay, 30 seconds.
So when you're executing code, there's going to be certain types that you can't deal with statically, but dynamically you can optimize for them, and you want to specifically find traces that are going to be run the most times or frequently and optimize for those cases.
Whoa.
15 seconds.
Okay, that was 15 seconds. So that was like too high level. Okay, fine, great. So that's 15 seconds. So let's dig deeper. So how does it actually work? So it starts in an interpretation, in basically using an interpreter mode. That's kind of the way that it used to work before that, right? So what's an interpreter? An interpreter is a program that takes. In this course, we're not talking really about interpreters, but this is actually another way to execute a language, right? It's that you parse the language. You have a representation of it, and you have a program that says, oh, I have an assignment here, let me run the assignment, and you actually update things, and it's just really, really slow. But you can interpret it, and you basically, so what happens? You interpret it through the code, and then what triggers compilation? You guys remember that?
Yeah.
Who wants to? Yes.
They monitor the execution, they keep a trace of everything that's going on, and whenever they identify a fault or something that the program spends a little time in, they compile it into native language, and they know the type in that.
Right.
Code.
So, but more specifically, yes.
They compile them. So the point is the traces are text specific, but the code is not. So what they do is when they identify hot code that is text invariant, they notice instead of having to go and interpret the typeset every single line within that hot code, they can just replace it by a trace, which is where text have already been pre-assigned, which is much faster. They just have to do a safeguard at each iteration to make sure that the text has not changed.
Sure. So, but all that is absolutely true. But if you start with at the beginning, right? I mean, the way it works is it actually doesn't collect. It doesn't collect traces yet. At the beginning, it's just like interpreting, and when it gets to a back edge, it kind of collects data of how many times the back edge is triggered. And when they pass a certain number of executions, let's say K, then it's going to trigger collecting of a trace the next time around the loop, and for them, K is 2. So basically, as soon as you basically pass, actually literally, because the first time you go and you see the back edge, as soon as you just go, it's almost like the first time you just see a back edge, you're literally going to start on the next iteration collecting. So sometimes the first iteration, you're actually not collecting. The second iteration you run of the loop, then you're going to collect the trace. And basically what matters is you're going to collect one pass through the loop at that point, and then you're going to get back to the back edge, and you're going to say, wow, that trace, I'm going to compile that, given certain assumptions about the type, as you said. And now you have this trace, and now you're set, right? Except what happens now. So when you go back, what? The types may have changed. Or you may actually execute, so either the types may have changed,
Or you may execute.
or you may have different branches, right? Because you picked a particular set of branches, now to go somewhere else. So in either one of those cases, really what it means is that you kind of fall back out to the interpreter, right? Whenever you basically are not, essentially what you're doing now is you go back and they have this thing called a trace cache. And by the way, this is actually not new. This actually has been done many, many times before. It's just that they apply it to JavaScript. So this is the idea of a trace cache, which is a whole bunch of traces. And when they see that, oh, there's a trace that I can run, you run the trace instead of interpreting, until you kind of, either the assumptions about the trace are incorrect, or you exit off the side. And what do they do then when you exit off the side? You interpret, and then you collect more data, more what is it called? Profiling data about which edges are being used. And if you get another hot trace, then you kind of end up having another trace on the side. So you have your main trace, and then they kind of patch in this other trace that you basically jump to. And so what's actually really cool is if you end up doing this trace, so what's cool about this trace-based thing? The first thing is that you actually can get complete compilation, right? Because you have a function which at the beginning you're just going to kind of start exploring little by little, and eventually if you hit all the paths, they're all going to get compiled and all linked in into this trace tree, and then everything will just be native code. It won't come back, it will never come back to the interpreter unless you have changes in the text. So that's one thing that's cool. What's the other thing that's really cool?
About their way, or in general, or the way they did it?
It doesn't matter. Who cares? You should tell me something that's cool about the...
Type-specific trace you can perform optimization.
So you can perform optimization such as what?
You can perform a whole bunch of them. You perform CSV, you convert flows to int, they do some sort of like dashboard elimination, store elimination.
Right, so basically once you have a trace, you can actually do a whole bunch of optimizations on it. And what's actually interesting is, so the type specialization is things like, okay, well, we know that everything's an integer here, so we're going to kind of just use integers instead of point numbers. You can also do really weird things. Like, for example, you have an assignment, and you may actually be able to delete that assignment because in that trace it's not used. But it may actually be used on other paths. So it's kind of this kind of the thing where the trace, you're specializing on trace. Yeah?
Make the argument that you get all the optimization passes that you otherwise don't in dynamic type languages. If you know the type is invariant, it's a type language now.
Right, exactly.
You get all of it.
Exactly. Actually, even better, it's even better than a type language. It's a type language without loops.
Sure.
Right? It's just straight line code.
Right.
No control flow. I mean, all the stuff that we were talking about, oh, there's control flow and merges and loops and all the stuff and termination, is like straight line code. You would have to really work hard at making your thing not terminate in that setting, right? I mean, like, because there's no loop. So the compilation of a trace is actually is relatively straightforward. The other thing that's really cool is that these traces can span multiple procedures and functions. So actually, you can actually have this thing kind of go into other functions and come back out, and statically you look at the JavaScript code, you have no clue where it's going to go, right? Because it's like all dynamically dispatched, it's all this kind of, they have these prototype chains in JavaScript. So, but at runtime you see where it goes, and you just collect that thing, and at the next iteration you go down a different path, and it's just going to exit that trace. So it's just going to continue on the trace as long as it's the same path, and if it's not, it's going to jump back to the interpreter, and the interpreter will just kick back in. Okay, so what else? Anything else?
You said it's cool that it compiles the whole thing eventually, and I'd say it's cooler that it only compiles what you're doing.
Right. But what's right? It's only compiling what you're doing, but what's cool about it is that the things get patched in.
Right.
In a way that if you actually really execute all your code, everything will get patched in such a way that eventually you get to literally everything. You don't go back to the interpreter anymore. Right? You basically, everything gets kind of patched so that you basically stay within native code and don't have to jump back to the interpreter. But you're right that in some sense another advantage is if they're paths that are not executed, then you will not compile. So you're not wasting effort. It's really literally like it's like you're only going to execute, like, you're only going to compile the branch that, like, it's like there's two branches, you only compile the branch that you're executing. And that should make sense, because it's like you may have an option turned on or off, for example, let's say in your email client, like, I don't know, what's an option like, or, I don't know. I have no clue. Like an option that, like an option that's
Option A.
huh?
Option A.
What?
A team that does it, so we won't be doing any other team.
Oh yeah. So what? You're in a team?
A team, like a black star team or something.
Right. So maybe you're part of a group or a team or something like that. That's always and it always likes to use. I'm not sure how that works though. Wait. No, I was thinking more like you know. Oh, okay. For example. Okay. I have an idea. Let's say it's an email client. On the client side that's running a browser, you have an option. Do you want to see a preview of your email, or do you just want to see like the sender and that you compact view versus, or how many lines you want to see? Do you want to see a 3 to 5 lines or no? And basically, based on that branch and whether you want to see a preview or not, it'll actually only compile the branch that actually you're executing based on what you set the option to be, right? Which is actually kind of really, really, really interesting. Cool. Okay, what else? Anything else? So performance, so they did a whole performance evaluation, and they actually even compared against V8, right? And what was interesting about was there anything noteworthy about the performance?
Just beat them on some of the times.
What?
Just beat them some of the times.
They beat, right, so...
They beat each other depending on the time.
So for a lot of these things, they're actually very similar, right? I mean, it's not like I mean, I guess there are cases where... So they give an explanation why they do so much better on some of these things?
Because their traces start at loop headers as opposed to, mainly they said because they're doing it at the loop granularity and no one else did.
Yeah, no, I mean, so I don't remember the details of this, like whether they explain or not. What?
Something about the tutorial.
Wait, everybody find that one. What? Wait, please.
That they're able to pretty much optimize everything into your operation.
Oh, I see. They're able to optimize everything into operations, and that actually leads to significant performance. So, what happens? Okay, so what's the drawback of? So what's kind of what are the negatives here? Are there negatives, or is this kind of?
They just didn't handle.
Oh, someone else. You guys have already talked. Okay, but yes. What? Okay. Right. So I mean, really, the reason why they can't. I mean, I think they can handle recursion very easily. I think the reason why they can't handle it is because they start their traces at loop headers. So really, they only see back at loop headers. But you can. I think if they wanted to start traces at the beginning of functions too, I mean, they could. So what they could do is, for example, start traces at the beginning of functions and then stop them when you get to a loop header. Although they wouldn't know it's a loop header. And that's part of the problem. But there probably would be. I mean, other systems actually use exactly such things. So I agree with you. It would be relatively easy to add recursion. Part of the thing is that recursion is probably not that important. I mean, in JavaScript, it's probably yeah. Wait, what? Yes.
So they have a problem with exceptions, especially.
So there's a whole bunch of things they don't actually handle, exceptions, and so for that, what do they do? What? Right, and so what do they just do interpretation then? Right. So
They did say we don't stop collecting traces, because the problem is not so much about the position, but they start taking huge traces at all the possible exception times, and then they overflow their trace.
Right. And you can get the same kind of thing happening if you can get an overflow, you can get too many traces too if you have huge amounts of context of different types. Right? I mean, you could probably write a degenerate case that kind of just every time around the loop, like a variable x kind of takes on a different kind of type context, and so as a result, it's just going to kind of keep on collecting these traces. And you can easily create like little limits and fallback plans to go back to the interpretation mode. And the point is, you always have the fallback here of this interpreting. That's kind of what, yeah.
And that could be actually true if you're traversing the DOM object. It could be any tag.
Right, so you're saying something where basically you have a loop, and every time around the loop you say x equals some DOM object element, and so that'll, right, now, right, that's a good point. Now, and one of the things is that I actually don't know what the performance, so I don't know what the performance characteristics of the DOM object access is, but I suspect that accessing the DOM object is relatively expensive because actually you have to transfer over to the C library. I mean, you have to transfer over into C line, sorry, C++ line, and so it's kind of this conversion and all this stuff, and so as a result, if you have code that does that, probably the overhead will be of doing this kind of transition from C++ line to JavaScript line will be, will mask the issues with the fact that you're kind of interpreting it.
Yeah, but JavaScript is generally not used for business logic or etc. It is used to manipulate the view. So a DOM object should play an important part in whatever decision they make.
JavaScript is used for like many different things.
Yeah.
Isn't it? I mean, it's used for like it's used. I mean, I don't know what you. Yeah, I mean, I don't know what business logic means. But I'm assuming that there is JavaScript code that does various kinds of validations of data on the client side before it's sent. I mean, you can insert validation of various kinds of things. But what your point was that the DOM access is important.
Yeah, because all the applications they have mentioned, like Gmail, etc., the maps, have to deal with refreshing the views quickly. It's like running desktop applications on a browser. So it's like the views refresh that much more slowly on a browser.
Right. Let's see. So what else? Anything else that's interesting about this?
I thought their blacklist was kind of interesting because the way they describe it in here is if they hit a case where it's basically unstable twice, then they blacklist it. Where I'm thinking, what about situations where it might be stable, like certain programs you can imagine, they're stable for some amount of time, and then they're going to lose stability, like they might need a couple iterations to switch, but if they do that twice, they're blacklisted. Or even though that might have been optimizable for like 10 minutes where it could have been cleared or something.
Right, so I mean, essentially, basically, the problem with all these things is that it's all best effort, and what they've done is probably done a whole bunch of, you just look at benchmarks, and they, for their purposes, in some sense, they had the easy evaluation, because for them, it's like, they were starting with something that was really, really slow. This is, this is how you can show good performance. Start with something that's really, really slow. And then you kind of, I mean, almost anything you would do based on the interpreter would be a lot faster. So there are probably ways that you can actually kind of tweak, and actually tweak your performance even better by doing these kind of things. I think the claim though is that it's basically things are it's very like bimodal. Either things are really like the same thing all the time, or it's like they're really way off, and it's just like as soon as you have two, it's really an indication that it's like really totally. Because your variable is either an integer. Right, if it's an integer, it's just always going to be the same thing, right? Or you have one of these like DOM things that's like really like will vary every time around the loop. So that's what I suspect is going on. But let's see. So, any other questions or comments on this paper? Yes.
The results of ISRA seem random. I mean, this is a blue bar and a green bar. They're like random numbers. There is no common line in sort of them.
What do you mean?
Right. So
you have cases where the blue line is really small and the green is like 20 times bigger, and then that's completely reversed, and you have the 12 outliers going through the roof.
right.
That's the section where they explain, like, the one that through the roof of the integer arithmetic speedups, other things were loop-based, while some were recursive-based, and that kind of explains the differences.
They explain the big blue line, but there is, I think there's the reason is not clear.
Right, so it's hard to it's hard to do it. I mean, it's like, why is V8 faster in some cases and slower in other cases? And that's a hard, I mean, it's a really hard question to ask, right, to answer. And I think part of the message here is not necessarily comparison with V8, but also just comparison with the baseline, which is the non-optimized. So basically, the fact that you're getting among large speed ups, I mean, that's kind of the main kind of thing.
Is there any follow-up where that combine the base of the blue and green lines, for example?
Well, I don't know the details of the fall, but so TraceMonkey there's actually several follow-ups to TraceMonkey, right? Like there's Jaeger monkey, and then there's something else monkey. They just keep on having these monkeys. What?
We all
Yeah,
get excited.
I don't know. It's like, so they have all these like different monkeys, and it's all
Crypto monkeys.
monkey-based, and eventually, so I mean, they're basically constantly improving things. You know, so that's. I mean, there's also this kind of really. What's kind of this bizarre thing that happens is that a lot of, I mean, basically, why are you optimizing JavaScript so much? I mean, at some level, it's like, there's a lot of the JavaScript code that you have running in your browser that's I/O bound, right? Because basically you have to, it's like your email client, there's a lot of connections, there's a lot of a lot of it is based on your connectivity. So there is a point at which you get diminishing returns on what you want. Now, of course, they have like, Google has these fancy demos where they can show that you can do like really fancy, like really, computations and graphics-based things and all this stuff, all in JavaScript, but it's not clear that those are necessarily that important or useful. So if we look at this paper, I mean, this paper and the one from that we saw last week, I mean, basically both of them are about dynamic compilation, and both of them are about specialization. They go at it from very different perspectives. This is about a trace-based idea where you kind of collect traces, and actually this work actually came from this other line of work that people have been doing on these kind of trace-based things. One of the things that you can actually use these kind of trace-based tools. It turns out that you can actually use these trace-based JIT compilers to actually take, say, x86 and compile it to x86, which sounds kind of weird.
What?
Right? You can actually take your x86 binary, because this is what it's doing here is converting JavaScript to x86. But actually you can start with an x86 binary and interpret it, and then collect traces, and then actually do the same kind of thing that they're doing on JavaScript, but you do it on your x86 code. And one thing that's cool about that is that you can actually optimize the assembly across dynamically linked libraries, across things that you would never have a hope of seeing statically. And you can actually also, in addition to that, you can actually also do things like control flow integrity, so making sure that you're not going to jump to weird places. You're not going to have buffer overflow attacks that make you jump into weird locations because you have this trace cache. So this trace cache kind of eventually gets you to a mode where you can check that if you don't jump to the beginning of a trace cache, something is really weird. And you go back to the interpreter, and then the interpreter can very carefully kind of do checks to make sure that you're actually jumping to the correct locations. The locations are stoutly known as being code. Yeah.
Like every single jump in place has to be like really expensive. Like performance-wise, it's not feasible.
Yeah, but so actually yes, you're right, that if you do it naively, it would actually be crazy, but actually there are very clever ways of doing it that actually get you, so there actually this thing called Dynamo Rio, which you can look up online, which actually does this kind of stuff. Basically very similar kind of trace-based compilation for x86 to x86, and while doing that, it can actually enforce various kinds of control flow integrity by making sure that jumps actually go to the right places and things like that. And actually the truth is you really only need to check indirect jumps, not direct jumps. So direct jumps you can actually just leave, it's just the indirect jumps you have to check. Yeah. Okay, cool, awesome. So this is okay. Do people like this paper? Better than last time?
Same.
Huh?
Same. They both target the same.
Same way? You mean you hated them both, or you loved them both?
I think they both target the same, a similar meta concept that neither addresses directly, though, where it's the concept that generic code should be more maintainable and easier to read, easier to understand, etc. And then they're saying, but we will, in the background, automatically, like, without human intervention, optimize it for you.
In a dynamic way.
Right. So it gives you, like, a lot of people compare things to optimized C code, but if you compare this to regular C code...
But most people don't think of JavaScript as being, like,
a language.
Yeah, as being like a language that really supports very good software engineering patterns. I mean, it's like or very high levels of abstraction.
I mean, there's a lot of software engineering patterns and whatnot that try to modularize optimization.
Sure. So sometimes actually, but actually that's I guess, so basically you're trying to say, actually you're trying to say something which is basically even more general than either of these two variables.
Right, that's fine with it.
Basically, like, there's this other idea which is that basically you should write your code in the beautiful,
Readable and correct.
software engineering kind of way where it's like readable and functional and not like you don't have side effects, you don't have like weird aliasing. It's very beautiful, clean, and understandable.
Provably correct.
And well, maybe provably correct, or it helps you reason about it. And then you have the compiler in the back end do all the optimization to regain performance.
Right.
Of course, that's not at all what happens. What happens in reality is people write their code originally and then they're like, oh, I think this is gonna be slow, so let me rewrite it this way, and they actually do all kinds of hand tuning, a lot of times at the detriment of readability and maintainability, and a lot of those things are actually completely ridiculous because the performance bottlenecks are not where you think they are, and so they're kind of they're optimizing too early. Absolutely. So that's right. Absolutely. Yes.
So this might be a wrong question, but
There are no wrong questions.
the trace cache has been part in the actual hardware processors for years now.
Mm-hmm.
So this idea of trace cache, why doesn't it automatically get done at a very low level?
You mean in hardware?
Yeah, in hardware. It's there. I mean,
Well,
they don't do all these optimizations in that hardware trace cache, but maybe indirectly they do those.
So okay.
How's hardware doing trace cache?
So let me just okay. That's a great question. So has anybody heard of this company called Transmeta? Okay. So some of you have heard of it, some of you haven't. So this is actually maybe a decade ago, or maybe there's this company called Transmeta that actually Linus Torvalds was kind of involved with, so it kind of became very like visible. And they were doing actually kind of something very similar. They actually provided, it was even crazier, they provided kind of an abstract, assembly instruction set. What I mean by abstract is that it's really just like, it doesn't exist and it's not implemented literally. What happens is then there's a translation layer that takes that assembly level thing, compiles it using exactly this kind of setup, which you trace-based stuff, and some of it is in hardware, some of it is not, and then actually does all these optimizations. And the idea was that because they would do this stuff, they would be able to get good performance while giving you much lower power, using much lower power. Now, I don't know where, so Transmeta is still, they got bought by actually NVIDIA or something, or Intel. Okay. So anyway, so actually there were people who were doing that kind of stuff, and you can do it. There is though, so I don't know the details of what the trade-offs are and why. Current Intel processors don't have that. They don't have a trace cache, right? So they actually collect like long instruction sequences in this way. That's smart, right? They have an instruction cache, but that's different. That's a very tiny, that's very small. This trace cache, it's like a huge data structure, right, where you collect lots and lots. This is basically, the trace cache is literally every piece of assembly code is in your trace cache. So it's like this massive data structure, right, that contains all of your code. The instruction cache is a very tiny thing that includes only the thing that you're currently executing that's really hot. So it's a different concept. But okay. Okay. Now what? Now we go back to what? We go back to data flow analysis. So I changed some settings on my computer so that it's not gonna, I think I changed the settings in a way that's gonna make it not switch the screen over. Let me see if it works. Okay. So this is where we left off last time. Actually, not quite here, but kind of conceptually where we were at. So we basically developed this idea of a global flow function, F. We had the small flow functions, which are individual nodes, and this is a big flow function that takes an entire array of results. So the results for all of the edges in the control flow graph, and then it basically applies in one big step all the individual flow functions for the individual nodes. Does that make sense? Any questions on this thing? So this is a big flow function. And then we saw that really what we want is we want to find a fixed point of f. In other words, we find m, and m is an array here, or map, so it's basically one piece of information for every edge in the control map. So we want to find something where we've gotten this fixed point, where m is equal to f of m. And the way we can do that is we start at bottom, or we start with an array of bottoms, and then we apply f, and we apply it again, and we keep on applying it. And if we set things up properly, we get this kind of situation where we start with bottom, and every time we call f, we monotonically increase, right? Every time we call f, we get that we go up in the lattice. And the reason why that's useful is because if we get this set up this way, then if our lattice has a finite height, then we're guaranteed to terminate. Okay? And what this thing is about, which is, oh my gosh, this is horrible. Let me not show you this. I'll show you this. Which is basically what this shows is that the only requirement you need to guarantee that you're kind of doing this, that you're basically going up the lattice as you're applying additional, iteratively, is that all you need is monotonicity. And monotonicity was right here. It's this thing, which is that if A is less than B, then f of A is less than f of B. And if you have this, then you know that bottom is less than f of bottom, and then you can basically know that if you apply f on both sides, by basically this is less than this, then f of this is less than f of that. You get f of this less than f of that. And then you can keep on doing this, and you get basically this increasing change. And as a result, you get this fact that if you have a finite height, is there like a b there or something?
Yeah.
What?
Yeah.
Oh man.
They only attack hair.
What?
They only attack hair.
They only attack what?
Hair.
Hair? What?
They think it's a hole. If it's dark hair, they think it's a hole, and then when they go to flight into the hole, they think they're being attacked.
What?
What? I've never heard that. This is the most
They
ridiculous
like
thing.
bright colors.
My cousin's a beekeeper. Like, he's a bee harvester, yeah.
They attack your hair?
If it's dark, so I'm safe.
Yeah, they think it's a hole, so then they feel like you're trying to trap it.
Cover your hair.
And then once yes, sir.
But what about your t-shirt? If the black t-shirt doesn't attack it?
The difference, I mean, it's probably would, but the difference is it's not going to feel like I'm trying to entangle it, where if it flies into my hair, it then feels trapped, and then it's going to sting me, and then,
It's going to sting your hair.
well, my head.
Oh, your head, okay.
What happens if it flies to, like, if you're wearing bright colors? It'll go, like, thinking you're a flower.
Yellow and blue.
So,
It's the yellow and blue,
Yellow.
and then gray sky.
Okay. So what do we do next?
I don't fight you, though. Just 'cause of that.
We'll just try and get nectar out of you.
Yeah.
So here's what we have. If f is monotonic, so if f is monotonic, then it means that finite height and line termination. And we don't need this outer join to kind of force the thing to keep on going in an increasing fashion. We just get it by this argument that we have right here. Okay? Which is that you can kind of argue that if f is monotonic, then finite height implies termination. There's also this side thing, which is that, of course, this big F, yeah.
This may be a not so good question, but does
Everybody, this is going to be the wrong question. No, it's a great question. Okay, go, come on.
I feel that F being a monotonic condition is just a little too strict. If, let's say, there is one particular point at which it just goes like against the monotonicity and then goes back to its own path, it might still.
So it turns out that actually monotonicity is not that. It's actually most flow functions that you write are monotonic. It's actually kind of it's kind of a weird thing for something to be not monotonic, because really what this means is that, so monotonicity really what it says is that the ordering in the lattice really means precision. So basically what this is saying is that if the input, basically really what this says is that F preserves precision, right? So it's like if you get a more precise, so okay, what does this mean? A is less than B. Less than or equal to B. Which one's, oh my gosh, hold on. Which one's more precise? Remember, because the ordering, so there's like, so wait, which one, okay, wait. There's bottom and top. So bottom is
More precise as you go up.
So bottom is optimistic. Okay, because we start with bottom, we start with the best possible answer, we keep on, and top is super conservative. Top is always correct. It's like if I ask you what's the correct result, you say top, it's like it'll always be.
It's not very helpful.
So precision, so the higher you go up in the lattice, the less precise you are. So basically, if you're lowering the lattice, you're more precise. So this is saying that A is more precise or equal to B. Oh my gosh. Basically, A is either the same precision as B or it's more precise.
Okay.
Right? And basically, so in some sense, another way to say that in English is that A is no less precise than B. That's kind of weird, right? But that's a very,
It's not.
A is no less precise than B.
No.
I mean, either A is the same precision as B or it's more precise. But you know that A is not like less precise than B.
Okay.
And so basically the idea here is that when you apply F, I mean, it keeps the precision, right? So what would be a violation of monotonicity? A violation of monotonicity would be you make the input to F more precise, and F gives you something less precise than it used to. Right? It's like you have an input to F and it gives you an output. You make the input to F more precise, and then the output becomes less precise. It's like, what? This is weird. It's actually kind of an odd thing, actually. So it's actually very common for flow functions to actually be to always be monotonic. It's usually the case. So that's and actually I should point out. Let me just say, actually, very important thing. This monotonicity is not the same. It's not the same as saying this. Okay, this is not the same. So we're not saying that F of A always gives you something bigger than A. It has nothing to do. We're not relating the input of A to the output of A. We're relating, if you make changes to the input of A, how does that affect the changes on the output? Sorry, changes the input of F, how does that affect changes on the output of F? And what this really says is that, like, if you make the input more precise, then F is going to be it's going to also be more precise. That's really what this says. Okay. So big F is, and by the way, that was a great question. That was a great question, because it actually allowed me to explain that. It's really good. So the other thing is that, remember this F, big F is a global flow function that operates on this big array. And originally we were talking about these flow functions at a node base. But essentially, if your local flow functions at the node base are monotonic, then the global flow function will also be monotonic. So that's kind of a side thing. So that way you only need to reason about monotonicity of your local flow functions on the node. Now, here's another benefit of monotonicity, and this is actually so cool. This is actually really, it's really awesome. So, basically what we saw is that if we start at bottom, and we apply F. If we start at bottom, and we know F is monotonic, and we apply, and we have a finite height lattice, we apply F at bottom over and over and over and over again, we're going to guarantee we reach a fixed point. Okay, so we're going to reach a point where you apply F, you get the same answer, right? So F, so we're going to get a fixed point, M is equal to F of M. Now, it turns out that with these things, you're not guaranteed to have a single fixed point. You may actually have multiple solutions to your set of equations. So there may actually be multiple solutions such that M is equal to F of M. Okay? So let's suppose that someone comes to you and says, here's a fixed point. I found a fixed point for you. Okay? And let's call it, what are we going to call it? We're going to call it FP. So that's a fixed point. So if someone comes at you and says, I guarantee this is a fixed point. Okay? So what does that mean, that it's a fixed point? It means that basically, what does it mean? That FP is equal to F of FP, right? Okay, cool. So we definitely know that. So we know that. So what else do we know? So we definitely know that FP is what? There's a squiggle sign here because FP, remember, this fixed point is actually an array, right? It's an array of facts, one fact per edge. So we also know this. Why do we know this? Well, it's just the definition of bottom, right? Bottom is, is less than everything. It's because it's the smallest thing. Okay, now what do we do? What should we do? What do you think we should do? Huh? Well, maybe we're done. But what can we do? What else can we do? So maybe you're happy. Maybe you're basically, you know what? If someone comes to me and gives me a fixed point, then you're happy. But I want to go further than that. Yeah.
Apply F to both sides.
So I can apply. So remember, F is monotonic. What that means that if something is less than something else, when I apply F on both sides, I'm going to get that is less than the other thing. So I can basically, I get that F of bottom is less than F of FP. Yeah? What's F of FP? It's FP. Because it's a fixed point, right? Cool. Now what do? We do it again. So we do it again, and we're basically going to get F of bottom is less than FP, and basically F of FP, which is just FP. And then we can just keep on doing this. And we keep on doing this, and we keep on doing this. And what happens? Are we going to run forever if we keep on applying F this way? No. What are we going to get here? We're going to get a fixed point. We're going to get the fixed point that we're computing, right? It's the one where we start at bottom and we keep on going up because we know that it's finite height, we know it's monotonic, so we know that eventually, as we're going to go here, we're going to go, this is our fixed point, the one that we compute using the techniques we've been talking in this class, using worthless algorithm, all this stuff. So, what does this say? It says that our fixed point is less than or equal to the fixed point that was given to us. Exactly. So what does this tell us? This is like cool. This is like so like awesome. Yeah. Our fixed point is optimal, and what does optimal mean? It's actually, so what we've done here is we said, well, suppose we have another fixed point. We've shown that our fixed point is smaller or equal to that other fixed point. Right? And so what that means is it's optimal, and another way to say it is that we found the least fixed point. Right? This is exactly what the definition of when you want to show that something is the least fixed point, how do you show that? You show, well, suppose I have another fixed point, and here we're showing that our fixed point is less or equal to that fixed point. So what we're getting is that we are guaranteed to find the least fixed point, and the reason why it's optimal is because we said how lowering the lattice are better results. Right? The ordering is such that lowering the lattice are more precise results. And so the fact that we're finding the least fixed point means that of all the possible solutions of our data flow, of our flow function equations, we are finding the best possible answer. Okay? If there are multiple answers, we're finding the best possible one. When we do constant propagation, as an example, I'm going to show you an example where actually this matters, that we actually find the least fixed point. Okay. Cool, so we're computing this control. Isn't it awesome? You guys are not impressed. You guys are not like...
I'm impressed by the Martian.
Oh yeah,
how do
they get the fixed point? They have magic. They just they just know stuff. So by the way, if you start at the top, what happens? Same thing, but basically we get the greatest fixed point.
Oh.
Okay, so if we start at the top, we're going to basically start at the top and keep on going down, and eventually we're going to get the greatest fixed point. Now, in some cases, the greatest fixed point and the least fixed point will be the same if there's only one fixed point. But if you have multiple fixed points, then one will give you the least fixed point, and the other one will give you the greatest fixed point. And in some sense, the way to also think about it is that when you start from the bottom, you're approaching the least fixed point from answers that are more precise and incorrect. So you're kind of always in this mode of incorrectness until you reach your fixed point. Whereas the other one, you start at the top, and you keep on going down, but you're approximating from above. So you're always at a point where you're more conservative than the actual answer that you're finally going to get. So basically, at any point in time, you can stop. Yes?
So if every time we start at the bottom and doing the same procedure, and even if there are more fixed points, how can we ever reach them? Because after our fixed point, we'll just fail.
So, sure. So first of all, you can start at top, which is actually sometimes useful in compilers that are time limited, like just-in-time compilers.
So you might do something else.
Right, you might do something else. In fact, I'll show you an example later where we're going to have a program where we're going to get different answers if you start at bottom or top. Okay. And there's actually another thing, which is that it turns out that you can actually randomly start anywhere in this lattice. Actually, you can basically pick any point in the lattice. And if you start at that point, it doesn't have to be bottom or top. Actually, you will, if you do the theory, it works the same way. You will eventually, well, at that point, the thing is, you're either going to go up or you're going to go down, but eventually, you're going to hit something. So yeah. Yeah. Wait, if you have the greatest fixed point.
Well, so you said that there can be more than one fixed point, right?
Yes.
So, there's no greater fixed point, for example.
And the least fixed point. I think we have two fixed points.
Given the greatest fixed point, and we start from the bottom, and we hit the least fixed point.
Yeah, we'll never reach the greatest fixed point, which is great. I mean, because we actually would prefer getting the least one. Yeah, I mean, if you start at bottom, you're gonna get the least fixed one, and you may get stuck there, and you're not gonna get to the greatest one. The greatest one is gonna be up here. You're not gonna get to it. If you want to get to it, you start at top, and you're gonna keep on going down until you get there.
If we start anywhere in the lattice system, do we know
It's a little bit more complicated. If you start anywhere in the lattice, it's a little bit too quickly. It's actually a little bit more complicated. Let me retract that, because it's actually the problem if you start at bottom or top is that you know that when you're at top, when you F up top, you're going to necessarily be lower. And that kind of allows you to bootstrap yourself in monotonicity and get this kind of connecting chain. But if you start in the middle, you can actually get the case when you apply the flow function, you can actually go sideways. And then you're not going to be able to apply monotonicity. So you can actually get this bizarre setup where you could possibly not turn it. But it's very unusual to start in the middle. Usually you start either bottom or top. Yeah.
Do we know the state that in the middle of the lattice to start from there?
What?
Do we know the state at those points in the lattice between the top and bottom to start from there?
Yeah, you can. Of course you can. I mean, there are. Of course, you can randomly generate a state. So actually, we'll see. This will become more concrete when we actually see constant propagation as an example. And we'll get back to this thing of we'll see an example. You start from the top, you start from the bottom. You're going to get different answers. Yes.
Yeah, another question.
Yes.
This makes sense when you consider a very sequential kind of a program, but let's say you have procedures and scopes going in. So you might have flow functions which might have variables increasing, then after a scope is over, the number of variables will decrease.
Right.
How does
So we haven't talked about stuff across procedures. Things across procedures are, I mean, there's a whole other. We're going to talk at length about that. For now, we're gonna assume that yeah, we're not gonna have functions. Actually, we'll have functions. We'll see. We're gonna deal with functions very conservatively. But within a function, I mean, you can always. I mean, so you can set everything up so that you can actually get those. I mean, it's not every program. When you think about it, it's really what's happening is every program point needs to go monotonically up, right? And so at a given program point, it's very unlikely that you're going to discover that, oh, you have 5 variables, and then all of a sudden later in your analysis, oh wait, now I have only 3. It's like, wait, what happened? What happened to those other 5 variables that you thought were there, right? So that's why it's going to usually go monotonically up. Or monotonically up in the lattice. Yeah.
Suppose you start at the top.
Yeah.
Then you do a set function. So it will go to the top or it will go down.
It will go, well, it could stay at top, but it could, but more likely than not, it will actually go down.
But the top is like the least precise function.
No, this is precise information. But actually, a flow function can actually still give you information on that. So remember, the flow function, so let me give you an example. Let's say the statement x equals 5. Okay, so after that statement, I know that x is equal to 5. It doesn't matter what came into that thing. It doesn't matter what the previous statement. I'm going to know whatever I started with, even if everything before was like totally, I had no information whatsoever. I had the worst possible thing. After that statement, I know I'm going to have 5. And that's how you can gain information from certain statements, even though you're totally at top. And we'll see an example exactly of that. So in some cases, f of top will actually give you top. But actually, in many cases, f of top will actually go a little bit one thing down. So let me just do a quick recap. So we started with the worthless algorithm for reaching definitions, and this is the thing that we wrote down. We had a empty thing here, and we had a union thing here. And this was meant to, we put this union thing here to make sure that all the edges go, all the basically information keeps on monotonically increasing so that we reach termination. Then we generalize the algorithm to lattices, so we basically put this bottom and this information here. So now this algorithm is generic. It's going to work on any kind of lattice, and the lattice can have various kinds of information, so it's much more generic. Then basically we wanted to remove this outer join while still guaranteeing termination. Right, so this outer join is the one that's guaranteeing termination. The question then was, can we remove this outer join and while still guaranteeing termination? And the way we did that, the reason about that is that we expressed our algorithm formally with this big F, and we saw that basically that we can express it as a fixed point computation. And then we saw that if F is monotonic, we don't need the outer join and we still get termination. So if F is monotonic, you don't need the outer join. You don't need the outer join to get this increasing chain. And if F is monotonic, the height of the lattice is finite, then your algorithm terminates. And on top of that, if F is monotonic, the fixed point you get is the least fixed point. Okay? So that's the summary where we're at so far. Does this summary make sense? So if F is monotonic, we don't need that outer join to make us keep on going up. It's guaranteed that if we start at bottom, we'll keep on going up. If F is monotonic and the height of the lattice is finite, then it terminates because basically there's only so many steps you can take up, keep on taking up. And then we also get the least fixed point. So if we start at top, so this is where we get the greatest fixed point. And here's another way to look at this that kind of may actually help you visualize it. So this is not, it's just a kind of it's an approximate visualization. It's not like this is exactly what happened, right? Because this is not, in lattice, this is not what happened. But this is with real numbers. So that's a function f from real numbers to real numbers. And so in some sense, what's happening here is you can think of this as bottom, and this is top, right? In the ranges of, so this is bottom here, and that's the top, right? So basically f takes something and it takes this whole array of things and it returns a new array of things. In this case, it's a function of real numbers. So what are the fixed points of this function? You draw a line. Right, the fixed points of this function are all the places where you have these intersections, right? Because these are points where, right, this is the X, and this is F of X, and they're equal here, right? Because this line forces these two to be equal. Does that make sense? That these are basically, so how many fixed points are there? There's 3. Right, there's this one, and there's this one. Now which one, so this is the least fixed point, and that's the greatest fixed point, right? So, if we start here, conceptually at bottom, so we start with bottom, and we say f of bottom, f of bottom, where's f of bottom? Oops. Oh. Why does it not work? Right, that's f of bottom, right? I mean, bottom is 0, so that's f of 0. Now I want to do f of 0. So the way you could do it is that basically if you project this here, you just draw a straight line and you go here. So that's f, this thing is basically f of 0. We'll just do 0 now instead of bottom. So that's f of 0. So what's this thing here? That's f of 0 too. Right, so it's basically we're looking at f of 0 on the x-axis now. Right, so this here is now f of 0 on the x-axis. And if I draw this line here, what's this?
F of 0.
That's f of 0. Right? And now, how do I get f of 0? Well, basically I project this thing onto this thing, and now here I have f of 0, right? That thing right here. And so, and then this point right here is f of 0. So you can actually see how, basically by applying f to the starting point and applying it repeatedly, what we're doing is actually doing this thing where we kind of bounce off, and eventually you can see that we're basically going to hit this point, right? And that's an intuition for this kind of fixed pointing. If you start here, what's going to happen? So f of 10, what's f of 10? Well, f of 10 is here, right? And how do I get f of 10? Well, basically I have to, so that's f of 10. If I project that here, now this is f of 10, right? That's on the x-axis. And if I see where f hits here, it's right there, right? It's right here. And so that's f of 10. And you keep on doing that, essentially the same zigzagging will happen, but you're going to hit this fixed point instead of this one. Okay? So this is just a way to kind of understand visually a little bit. This is really not what's happening. This is just kind of a visual way to kind of to get a sense of what's going on. And one last thing before I answer the question. Note how here, when I do f of 0, f of 0 is greater than 0. And here, f of 10 is less than 10. So there's no relation between the input and the output. In some cases, you pass in something and you get something that's bigger, and in some cases, you pass in something and you get something that's smaller through f. That's not what monotonicity is. But this function is monotonic, and the reason why the way you can see it's monotonic is because it's actually increasing. Right? It's always increasing. The slope is always positive here. Okay? Yeah.
Are all lattices guaranteed to have a reachable fixed point? Because in this case, we were talking about real numbers, we'll actually never get to the
Right.
So you need it to be discrete and
Exactly. But you know why? Because this thing, because this doesn't have a finite height. That's the problem. Right, because they're real numbers. If there's an infinite, so basically, what is finite height? Finite height means that the longest path from bottom to top is finite. Okay. In this case, the longest path from 0 to 10, which goes through elements of the lattice, is infinite. So if these were integers, though, then you probably get, but then it's a little more complicated to draw it because it's not a smooth curve. So you're absolutely right that's why we need, that's exactly why we need the finite height requirement. Otherwise, you can keep on going, like keep on applying it and never actually reach the real fixed point, right? That's a great observation. Okay. Any other questions on this? Yes.
I just want to check my understanding of what the input of that. Is it the true definition of all the edges? Or? So
in this case, the input is just a floating point number, but the big F in the algorithm. So in the theoretical formalization, the input to capital F is an array that contains a piece of information for every edge in the control flow graph. So it basically takes the whole state of your solution and gives you the next state of your entire solution. That's in the formalization where we're talking about fixed points. In the implementation algorithm, we actually are doing the flow functions locally on one node at a time, and we do this kind of worthless algorithm. But when we formalize it, we do this thing where it's this whole array, and we keep on doing this array kind of one step at a time. Yeah. Does that make sense?
Yeah, that makes sense. So in order to show that the whole termination, you need to show that its local update is equivalent to the global update.
Right. So basically, you need to show that basically, if the local flow functions are monotonic, then that global flow function that takes this one step like this is also monotonic. But that's actually relatively easy to show. If each one of the local flow functions are monotonic on a node, it's relatively easy to establish that on a big array, it's going to be monotonic. Cool. Graphically, I'm actually going to skip this. I showed this to you before. There's another graphical way of looking at it, but I'll show it to you again just quickly. But another way to think about it is that you start at the bottom here, and you just keep on going up the lattice until you basically kind of have a loop where you apply F and you get the same answer. Okay, so that is the end of that. So now we are going to do some examples. Okay, constant pop. Pay attention. You know why? Because this is going to be on the midterm. Not this. But you're going to have to write flow functions on the midterm. So, in fact, I'll tell you, one of the biggest parts of the midterm, you're going to have to define your own analysis. On analysis, you have to write the flow. So we're going to do several examples of this, but this is kind of, you should listen and pay attention to how we set up this stuff. So, the first thing we're going to do is figure out our domain. The domain is basically the domain over which the lattice is defined. So what D is going to be is the set of all elements in our lattice. Okay? And I'm going to just set this up for us. I'm just going to say what it is, even though later on we're going to do it slightly differently. We're going to do it in a way that's very similar to reaching definitions. So constant propagation is trying to figure out if a variable has a constant value, and so what we'll do is we'll just have every element in the lattice will be a binding telling us x is, for example, 5, y is 10, and like b is 25. So this will be a piece of information that we could have at an edge. Okay, so every edge will have a set of these bindings that tell us what variables have what value. And so the way to formalize that is that we're going to basically say that it's a superset, it's a power set lattice, which is basically the power set, actually I'm not going to do this, I'm going to just do the power set of such that x is in var and n is in what? N is basically, yeah, let's say the integers. It could be more complicated, we can have strings and stuff like that, but let's say for this thing going. So basically, this is a power set of basically all the bindings. So basically, what this power set does is it constructs all the sets that are subset of this big, huge set. And this set is a huge set, right? It's a huge set because we're talking about all possible integers, okay? So in reality, actually, the set is finite, but it's huge. It's finite because there's only a finite number of binary representations of numbers that we want to care about. But but anyway, so let's just assume we have this representation. Does this make sense? So at every edge, we're going to compute a set of bindings of the form, x goes to some number, y goes to some other number, and things like that. So how do we write the flow function? So let's write this flow function for x gets n. So assignment, so we have this input information, so what do we do? Basically, we just say this, right? We now know that x goes to n. Right? After this assignment, we know that x is n, right? Right. Okay.
Another one before.
Whoa, okay, wait a minute. So, okay, so there's a slight trickiness. What if we had what if x were mapped to something else in the input? Right?
Right.
Then we don't want to map it, so basically, we don't want to map x to two different things, right? If x were 5, and then we do x is 6, now we know that x is 6, it's not 5 anymore. We have to remove the previous binding. And so the way we can do that is that we just say, we're going to remove basically anything that, we're going to basically remove this set, which is x mapped to anything. So we're just removing all the bindings of x. And then we're just adding the x goes to n. Cool. What about this? So now we have minus what? So same thing. So now we have two options. We can either be lazy, and if we're lazy, we can just stop here and say, that's okay, right? It's like, you know what, I don't want to deal. And actually, that would be fine. It would be correct, right? We just would not, I would just remove all information about x, and really what this would be equivalent to is saying, this is too complicated, I don't want to deal with this operator. It's like, oh, whatever. But let's say we want to be a little bit more precise.
Are y and z constant integers?
No, they're variables.
Okay.
So x, y, and z are variables. And by the way, these are, let me also clarify, notice how these are capital. It's very important that these are capital because these are patterns, right? This is basically this flow function works for any statement in your program where a variable is assigned some constant, right? So if I have in my program, I'm going to have something like a equal to 5. Lowercase a is equal to 5, and so basically the way I'm going to know how to handle the flow function for this is I'm just going to I'm seeing the pattern here, which is now this capital X, which ranges over lowercase variables, is going to be a, and this n is going to be 5. So here I'm writing essentially the flow function for this sequence pattern, right? So all statements of this form, where you're assigning a variable, or you're assigning a constant, literal, into a variable, that's what this flow function is for. Does that make sense? Okay, so what do I do here? What can I add in? If I want to add something in, yes?
We continue on x point to f of y of operator f of z.
Well, hold on. So really what I want to say is, if y is constant and z is constant, then I want to basically make x constant. So how do I test whether y and z are a particular constant? Inside of int. That's the only way I know they're going to be constant here because that int information tells me that, right? So basically, I'm going to add, so if I have y goes to, let's say, n1, which is some constant, and that's in, and I also know that z is in n2, and that's in. So if I know these two facts, if I know that y arrow n1 is in, and z arrow n2 is in, both of those things have to be there. Then I know that both y and z are constants, and I know what those constants are. And so now what do? Well, basically I can add x maps to, in some sense I'm going to put brackets here, it's really hard. Really what I want to do is my compiler is going to evaluate this n1 off n2. Right? It's literally going to take, it's going to eval this constant off this other constant, and it's going to create this new constant, and it's going to basically say that x now maps to this. So basically, what I have is you can write it this way, which is that x maps to the evaluation of this n1 off n2 if y is mapped to n1 in the input and z is mapped to n2 in the input.
Just to be clearer, then, n is a constant, and y and z are variables that you're saying can be evaluated constant.
No.
Or represent constant.
These are variables, and these are constant literals. The constants.
Okay. Right.
Right. But they're uppercase, because what this means is that this n, this will work for any statement in the program where this is a constant like 5, and this is a variable like a, b, c, w, whatever.
Yeah.
And this will work for anything where I have a variable here, and a variable here.
So our notation between variable and constant, though, is
Absolutely.
not.
So you're right. So we're using notation to differentiate between variables and constants. So this n will stand for constant, and this thing. So absolutely, you're absolutely right about that. Okay, good news. It's over. Well, some sad news. Yeah. Oh, we're not dealing with loops yet. This is just a flow function for individual statements. The way we deal with loops is our iterative data flow analysis algorithm will keep on iterating over and over until we reach a fixed point. This is just dealing with the flow functions for individual statements. Absolutely. So, okay.
What if y or z not defined in the scene?
What if y or z are not defined?
Yeah.
So,
There are possibilities that.
right.
That's a bug.
Well, then you probably wouldn't have that y is arrow is. So you would not get this information in the input. Your analysis will not figure out that y is a constant, a particular constant here, right? Because if y is not defined, then it can't be that constant.
So you mean we can't do an analysis?
Cool.
No, you can. It's just that you won't be able to figure out anything about x.
The union becomes the null set, right? You still removed all other x's. Like you still do n minus the.
Oh yeah, you'll still do this. You'll still do this, and this will not union anything because you want to think about y or z.
Right.
So we should write something out here.
No.
What do you mean?
I mean, what if y or z is not defined in the in? So in the answer, we might need to write something else.
No, it's not that it's not defined. It's not in the in set. The in is a set of these things. In can be the empty set, for example. If in is the empty set, you have no information about any variables. In fact, that's what we'll have the beginning of the program be. We'll set in at the beginning as you know nothing about any of the variables. Because you don't know anything about constantness of any of the variables, right? You only get constant information if you see an assignment. So if the variable is not declared whatever, it doesn't matter. You just don't know any information about it. So, yeah. And we'll go through an example next time. Okay. Okay, we got to go.